Hey guys, I'm Amateur Chemistry. After a very long break in uploads, I'm going to talk to you today about rockets. More specifically, what propels these marvels of engineering into space. You ever wondered why these space shuttle main engines have clear blue exhausts, while rockets like the Falcon 9 have bright orange ones? Why some rockets seem to change color as they fire? The answer is more complex than it may seem. Let's start from the top. Rocket engines work by combining an oxidizer and a fuel. Most modern rockets use liquid oxygen as an oxidizer, but some, like Russia's Proton and China's Long March 3, use dinitrogen tetroxide, a highly carcinogenic and very reactive source of oxygen that's responsible for the red plume you see hanging over Chinese villages when they dump their first stages over land. Yeah, that's real.
Fuels, on the other hand, are a subject of much debate. A common fuel used by rockets around the world is hydrogen, which is used by the massive, and I mean massive, Delta IV Heavy, Europe's Ariane 5, and the upcoming SLS rocket. Hydrogen has a very distinctive clear blue flame, but don't be fooled by the Delta IV's red flame, it's still fueled by hydrogen. It's just that the RS-68 engine is not actively cooled. So that red is actually the engine slowly disintegrating itself. Although hydrogen is the best rocket fuel on paper, due to its low molecular weight, which translates into a higher fuel efficiency, or specific impulse, it has literally tons of drawbacks. First of all, it is much less dense than comparable fuels like kerosene and methane, and this means any tank containing hydrogen must be 6 times larger than those carrying an equivalent amount of methane. Hydrogen is also liquid at much colder temperatures than other fuels. This makes cooling liquid hydrogen a much harder task. In fact, it was a broken off piece of insulating foam on the shuttle's hydrogen-containing external tank that caused the loss of the Space Shuttle Columbia and all 7 of her crew. And if this wasn't enough, hydrogen has yet another ace up its sleeve. Being the smallest atom on the periodic table, consisting of 1 proton and 1 electron, it has a nasty habit of leaking through tanks and engines, meaning more insulation and engineering precautions. Just take a look at how much more complex the hydrogen burning side of the Space Shuttle main engine is. Now, this doesn't mean that hydrogen is all bad. It is massively more fuel efficient than other rocket fuels, although it often lacks the necessary thrust to combat gravity, which is why you see it paired with low-efficiency, high-thrust solid rocket motors. But it really shines as an upper-stage engine meant for in-space maneuvers, where its efficiency can be given time to work. Think of a first stage as a monster truck. It's inefficient, but nothing else can match its power, while an upper stage is more like a Kia Optima. You aren't buying it for its acceleration, you're paying for efficiency. All this means that the industry is slowly moving away from hydrogen-powered first stages. This brings us to the mainstay fuel of rocket programs around the world, RP-1, Rocket Propellant 1. Don't let the acronym fool you though. This isn't some obscure fuel found only in the aerospace field. It's actually just highly refined kerosene. That's right, the same thing used to power this also powers this. It's been used on the Saturn V moon rocket, SpaceX's Falcon 9, ULA's Atlas V, and Russia's Soyuz and Energia, which launched the often forgotten space plane Buran. And it certainly deserves all this popularity. RP-1 is dense, it's a liquid at room temperature, and offers a reasonable efficiency, although it's still much less than that of hydrogen. To add to this, SpaceX super chills its RP-1 down to near its freezing point, although it's already a liquid at room temperature, to make it 3 to 4% denser. When it comes to rockets, every drop really does count. RP-1 and oxygen burn to give a bright and opaque yellow-orange flame, very similar to that of a candle, and for many of the same reasons. But there is a reason that RP-1 is not the fuel chosen for SpaceX's upcoming Starship and Blue Origin's New Glenn, which are coincidentally both reusable. When you burn RP-1 with oxygen, incomplete combustion causes coking, or deposition of carbon polymers inside the engine, which is a massive pain for anyone looking to reuse engines without lengthy inspections. Enter methane, the next generation fuel that's being adopted by SpaceX, Blue Origin, and ULA, whose new Vulcan rocket is using Blue Origin's BE-4 engine. Its advantages are more nuanced than those of RP-1 and hydrogen. It's more resistant to coking than RP-1, making it more appealing to those looking to reuse their engines. Otherwise, methane is pretty comparable performance-wise to RP-1, but with one other advantage. It can be synthesized on Mars, because carbon dioxide can be combined with hydrogen to form methane through the Sabatier process, which is key in SpaceX's colonization plan with Starship. One final fuel deserves mention here, UDMH. While it isn't used in any American launch vehicles, it's used, in combination with dinitrogen tetroxide, to launch the aforementioned Proton and Long March 3. It's just as carcinogenic as its opposite number, but its scariest quality is that when the two combine, they spontaneously ignite. The pair are hypergolic with each other, which is an attractive quality for those looking for a reliable engine. Those assigned to work on them, however, probably don't feel the same. You'll be able to distinguish UDMH and NTO by their distinctive red-orange exhaust color and red plume that's characteristic of nitrogen compounds. Both UDMH and NTO are liquids at room temperature and can be stored for decades and launched in minutes. This makes them perfect for nuclear missiles that need to be on call 24/7 with minimal human input. If you look closely at a space shuttle main engine's exhaust, you'll notice that the exhaust is briefly orange before it gains its blue color. This is because of an interesting engineering problem called a hot start. Hot starts happen when you burn an engine oxidizer rich, meaning all the fuel is consumed in the reaction which makes the combustion chamber extremely hot. In order to solve this problem, the engineers at Rocketdyne made sure that the RS-25 engine would start fuel-rich. Just take a look at this chart showing the positions of various valves during engine startup. The main fuel valve, or MFV on this chart, opens and reaches a full open position almost 4 seconds before the MOV, or main oxidizing valve. This fuel-rich environment leads to an incomplete combustion where the hydrogen is starved of oxidizer, and the lower energy leads to the hydrogen emitting a lower energy wavelength of light in the orange spectrum. And then, as the ratio of propellant to oxidizer moves closer to a stoichiometric or balanced ratio, the flame becomes more transparent and blue. The Falcon 9 Merlin engine burns RP-1 and oxygen, so it should have a candle-like yellow flame, right? But as you can see, the rocket flashes green for a split second before it gains a typical yellow color. This is because the Merlin does not depend on dedicated ignition plugs. Rather, there is a hypergolic mixture of triethyl aluminum and triethyl borane that is injected into the combustion chamber. Called TTEB for short, this mixture is not a rocket-exclusive igniter. It also ignites the turbojet on the SR-71. Another interesting feature of rocket exhausts are Mach Diamonds, which are high-pressure areas of the exhaust being forced together by atmospheric pressure. In simple terms, the goal of a typical converging-diverging rocket nozzle is to exchange the extremely high pressures of the combustion chamber into extremely fast exhaust that matches the pressure of its surroundings. This is why vacuum nozzles are so much larger than their sea-level counterparts. They are able to expand the exhaust all the way to near vacuum in order to get maximal efficiency. On the other hand, sea-level engines must strike a balance between the expansion of the exhaust and what is called combustion instability, where the flow of the exhaust is actually pushed away from the rocket bell and can very easily destroy an engine due to the massive stresses this places on it. This expansion means the exhaust coming out is actually a lower pressure than the surrounding sea level atmosphere. But this is intentional because as the first stage rises, it encounters lower pressures, meaning that while the nozzle is overexpanded at sea level, it will be underexpanded at stage separation. You can see this over the course of a Falcon 9 launch, where the exhaust blooms out like a flower as the first stage gains altitude. Chemical rockets are not the only way to move around. However, especially in space, where the environment matters less than even here on Earth. Technologies like nuclear thermal propulsion, which uses the heat of atomic fission to accelerate hydrogen atoms to incredible speeds, are currently being funded by DARPA. Ion drives, which use electromagnets to accelerate xenon gas, have been used to propel spacecraft for decades. And the future holds even more exciting propulsion options. Nuclear pulse propulsion, which detonates shaped nuclear bombs behind a spacecraft, fusion engines, reflective sails powered by massive lasers, propelled by nothing except for the momentum of massless photons. The world of rocket science is no easy thing, and things get really technical really quickly. But it's a rewarding feeling to know you understand the science behind some of the most complex machines on and off the planet. And I hope this channel can add to all the great work being done to demystify rocket science. I'm Amateur Chemistry, signing off.